Hey, Algebra 2 honor students, this is going to be Unit 3, Day 3, and we're looking at today, talking about even and odd functions. Okay, so this is on page 10 in the packet if you want to take that out and start taking notes. So at the very top, we're talking about some rules for inputs and outputs, and that's what even and odd is really all about, is analyzing inputs and outputs and seeing if there's some sort of connection and relationship that would allow us to determine if something's even or odd. So we're going to look at functions today that may be linear, quadratic, exponential, and we're going to be able to classify them as being even and odd based on some symmetries that we notice. So the main idea is in this box up here, it says a function is classified as even if the following is true for every value of x in the domain of f of x. And I'll tell you something's even if f of negative x is equal to f of x. So essentially what this means is if I plug in x or I plug in negative x to the function, that the output y values are the same. So for f of x and for f of negative x, if those are in fact equal, it shouldn't matter if I plug in 2 or negative 2 to the function, the y values will be the same. If I plug in 7 or negative 7, the y values will match. Meanwhile, in the second instance, a function is classified as odd if what's true. In this case, we're going to find that f of negative x is equal to negative f of x. If that's true for every value of x in the domain, this part right here, then we would find that it's classified as an odd function. And basically the correspondence here is that if you were to plug in an x value and have a y value on the graph, that should correspond with the same negative x and negative y value on the graph. Okay, so here, x and negative x produce the same y value, but for odd, it's that xy point would have to correspond with negative x and negative y in order for us to be an odd function. So let's go ahead and analyze these two cases right here. We're going to analyze whether they're even or odd in 3 different ways. One way is numerically, and I'll tell you numerically is actually just looking at a table. So we're going to use the calculator to generate a table of values here in a minute. I'll show you the algebraic approach next then. So the algebraic approach will be taking a look at, does it match one of these criteria in our definitions for even and odd? And then we'll take a look at the graph and hopefully be able to make some connections between all 3 of these ideas. When we go to make a table of values for each of these, let's just go ahead and try going from -2 to 2 for both. And then analyzing some pairs of coordinates and seeing if there's any patterns to establish here. I've actually already gone ahead and typed both of these functions into y equals, and you could do them at the same time if you'd like. So I have x to the 4th plus 2x squared plus 5 up here, and then 3x to the 5th minus x, just checking that those are what's written down there. So if we go to the table right now from -2 to 2, boy, those y values really grow fast for this function. But from -2 to 2, we're getting for the function f of x, the corresponding y values are 29, 8, 5, and then it kind of repeats on the other side. We get 8 and 29 again. This kind of looks similar to what we would see in a table for a quadratic function, right, where we have kind of that turning point. But notice how this is an x to the 4th equation, which maybe in the end kind of looks like an x squared anyway. But here's what we got for our numerical table for what we had on the left. If I just kind of take a look at what we have for the right, 3x to the 5th minus x, when x is -2, the y value is -94 up here. And then we get -2, 0, 0, 1, 2, and then this was 294. All right, so can we make any conclusions based on these tables? Do we have any cases where f of x and f of negative x have the same y value? So when I plug in x or negative x to the function, let's look at this first table. Is that true that if I plug in x or negative x, the y values match? Well, they certainly do for the input of 2 and -2, those y values both match of 29. They even match for the inputs of 1 and -1, don't they? Okay, we can't clearly test it for 0, but for any other pair of corresponding terms, if I were to test -3 and +3, these relationships are going to hold true. So since xy corresponds with the point -xy, the conclusion in this case is that f of -x is equal to f of x. Okay. And what we know about this function then is we've already determined that in part A, this is even. Okay. Just based on the table. Now we're going to confirm this in two other ways in a moment, algebraically and graphically. But taking a look at the numerical table over here, does that even relationship hold true? Does f of -x equal f of x? Not quite. When I look at the corresponding positive and -2, the outputs are not identical. And that's what has to be true for even. These y values would have to be the same, whether I plug in x or I plug in -x. But what is true is when I plug in x and -x, it corresponds with y and -y. And that is true for an odd function. So if you have that, the point xy corresponds with the point -x, -y, then that's the conclusion that we would draw to know that this is an odd function. So for this odd function, what we can see algebraically is that f of -x is equal to -f of x. Right? If f of 2 is 94, what's f of -2? It should be the negated version of this y value, which it is. Okay, so that's how we interpret this function-y notation here. Okay, so if f of 2 is 94, does f of -2 equal -94? Yes, and that holds true for all the other coordinates here. So here's what we're going to be seeing as far as the table is concerned. This is what you'll see if it's an even function. And then on the other hand, this is what you'll see if it's odd. Let's talk about the algebra end of things then. To do some algebra, what we're going to do for confirming that this one's even is we're going to compute what f of -x is. How do I do f of -x in the original function? It says take all your x's and replace them with a -x. Okay, so when I do that, I would get -x to the fourth plus 2 times -x squared and then plus 5. Now, what I'm hoping you remember is if you raise a negative to an even exponent, a negative times itself an even number of times is going to become positive. So -x to the fourth power is actually the same as x to the fourth. Similarly, -x to the second is just the same as positive x squared. So that's going to stay plus 2x squared in the middle. Nothing happens with the 5 at the end. And notice how I've just confirmed that this equation is the same as what we started with. So the conclusion is that f of -x is actually the same as f of x. That's a quick algebraic test to show that this is an even function. So how am I going to algebraically confirm odd? Similarly, let's do f of -x on this side. So that would be 3 times -x to the fifth minus -x. Now, on the other hand, if raising a negative to an even exponent made it positive, raising a negative to an odd exponent should make this coefficient out here negative. So this is going to become -3x to the fifth. And when I negate -x, that's now positive x. If I compare this to the original equation, notice how these are not a match. So what do I know? I know that it's not even. I know that f of -x and f of x are not the same. However, what would the equation negative f of x look like? If I negate f of x, that's just like negating everything on this side. That would be -3x to the fifth and then plus x, right? If you negate both of those terms. And if these two things match, what we now know is that f of -x is the same as negative f of x, making this as an odd function. So even though this is a little bit more abstract for us, I think tables, it's a little bit more concrete. We have specific numbers to work with. You should feel by the end of this lesson confident doing both techniques, showing it algebraically, but maybe also using a table of values to illustrate this. Now, by the way, thinking about what the graphical representation is, how can I just look at a graph and know what's happening here? What we're saying is that whether I plug in x or -x, those two y values are the same. So what type of transformation is that? That f of x and that f of -x? So if x and -x have the same output, I'm hopefully what you're thinking here is that if you were to graph this, you're actually going to get something that looks like this. And graphically, if something is an even function, what that means is that it is symmetric about the y-axis. So that's a really important connection to make. If you have a graph of a function and it has y-axis symmetry, it's an even function. So what's going on for the case where we have an odd function then? It's not quite going to be y-axis symmetry. It's also definitely not x-axis symmetry. Because remember, if it has x-axis symmetry, if it was symmetric about the x-axis, it would fail the vertical line test and not be a function at all. So what's going on for an odd function, I'll show you what the graph looks like here. The graph of this one would look something like this. Okay. And maybe that key point that I just included there is helpful to you, but if you have a point x, y, and it corresponds with the point negative x, negative y, if you have an odd function, it has origin symmetry. Okay, point should be symmetric about the origin for odd functions specifically. And when you reflect through the origin in geometry last year, you would have x, y points that would become negative x, negative y coordinates. So it has that connection to what you learned about reflections in geometry as well. All right, so three really kind of different approaches. We have tables, the numerical approach, the algebraic approach, the graphical approach. You know, this whole idea of having these multiple approaches is so important in so many other facets of mathematics. You'll do this again in pre-calc. You'll do this again in calculus, just having multiple ways of approaching a problem. And I think some of them are really nice and visual, like these cases. Okay, so if you're a visual person, you like the graphical way. But I also want you to feel comfortable, again, this algebraic, this maybe a little bit more abstract way. We're going to hopefully become more and more confident with that as we go along. All right, let's go ahead and take a look at example 1 on the top of page 11. So example 1 says, consider the partial graph of f of x. So we're only seeing part of the graph. Sketch the other half if the function is, first of all, even. So what we have to remember is that if the function's even, that f of negative x would equal f of x. So how is that going to transfer? It means that when I have the x value of 3, if the output is 1, 2, 3, 4, 5, then when I plug in negative 3, the output should also be 5. And similarly, when I plug in, this looks like it must be at 4, 5, 6, 7. When I plug in 7 for x, if the output is negative 2, I should get the same thing when I plug in negative 7 for x. We should get an output of negative 2. Okay, 0, 0 is going to stay in place there. So to complete the rest of this graph, it's actually going to look like the letter M. Here's what the graph will look like if it's even. Oh, and by the way, what did we just decide about even functions? If it's an even function, it should have y-axis symmetry. So you actually could take the right side of your graph and just kind of flip it over the y-axis, but hopefully it would match this criteria anyway, that f of negative x and f of x are the same. So that's what part C was kind of jumping to here. What's the symmetry that's happening? All right, now we're given the same exact graph starting on the right side here, but now we're looking at an odd function. So now for odd functions, f of negative x would correspond with negative f of x. So what that means is the point xy is going to go to the point that was 3, 5. That's now going to correspond with negative 3, negative 5, which is, if I've counted correctly, down here. Okay, the origin point's going to stay in place, but the point 7, negative 2 is now negating both. 7, negative 2 is now negative 7, positive 2. So you're going to get a resulting graph that looks something like this if it has origin symmetry, meaning that it's odd. So for odd functions, the conclusion is it should be symmetric about the origin. Okay. So I kind of like those questions, kind of giving a partial graph there and thinking about what would the other side look like given that the function's even versus what it looks like if it's odd. I think you're going to do really well with example 3 because you should be familiar with what this graph looks like. But there are two different parts. There's a part A, thinking about it kind of from a numerical perspective with a table, and then there's a part B with a graph that you're going to sketch that you're going to use to confirm what you have in part A. So you're going to determine, is this function even, odd, or maybe it's neither of the two. Okay, because it doesn't have to be even or odd. We certainly can think of functions out there that don't have y-axis or don't have origin symmetry. Let's turn to the next page. So page 12, we have the function g of x equals x to the third minus 4x. Let's use our calculator to get the table values here, and then see if based on that table we can confirm yes, it's even, or yes, it's odd, or maybe it's neither of the two. Okay. So let's go back to y equals. We'll adjust this to have x to the third, and then minus 4x. And if I jump to the table there, when x equals -3, the y value is -15. When x is -2, we get 0. At -1, we have 3. 0, 0 is a point on the graph, and then we get -3, 0, and 15. Okay. So once we fill in the table, we should be able to, since we have a decent amount of x and -x pairs, analyze the corresponding y values and decide, is this even, is this odd, or is it neither of the two? So if we take a look here, 315 goes with -3, -15. 2, 0 is a little bit tough to compare to -2, 0, but let's check out when x equals 1. 1, -3 goes with -1, +3. So these x, y coordinates correspond with -x, -y, which means that f of -x is the same as -f of x. This is definitely an odd function. And what we should be able to confirm then in part B is if I were to graph this right now, we should be able to confirm that we have origin symmetry. So without even looking at the calculator, I know that this graph hits the x-axis at -2, 0, and then also +2. And the axes are set up really nicely for us here because if you take a look, here's -4 and here's +4. And at -3, the y value is way down here at -15, which is already labeled for us. How nice is that? And then at +3, the y value is up here at +15, so we can put that point on the graph. And when what's happening at -1? -1, the y value is 3. We'll do that approximately here. And then at +1, we're at -3. So if you start connecting these points, you're going to get a graph that looks something like this, okay? And it doesn't have to be perfect, but definitely once you've plotted it, you can see that we have this symmetry through the origin, and you should be able to confirm that if you hit graph right now on your calculator, okay? So, last couple questions here. Number 5, is the exponential function 2 to the x even, odd, or neither? Support your argument with numerical and graphical evidence. So numerical is thinking about this in a table sense. Graphical evidence, of course, is making a table, or sorry, making a graph of the function. Don't we know what 2 to the x looks like? Isn't this a parent function we're familiar with? It's an exponential function with a horizontal at y equals 0. Okay, if you don't remember exactly what it looks like, I guess we could fill in that table real quick. I'm going to do -2, -1, 0, 1, 2, and see what happens. Let's start on the positive side first, because that's actually easier, I think, for us. 2 squared is 4, and 2 to the first is 2, and 2 to the 0 is 1. And going backwards, remember, 2 to the negative first is not -2. It's actually 1 over 2, 1/2. And 2 to the negative second is 1 over 2 squared, which is 1/4. So here's my table. When I look at x and -x, do those y values have any sort of correspondence that would make this even or odd? And the answer, hopefully pretty quickly for you, is no. This is neither of the two. It's not even, it's not odd. Okay, when I plug in x and -x, we don't get the same y values. xy doesn't go with -x, -y. If you were to plot this function 2 to the x, I'm hoping you remember it looks like this. Definitely not symmetric about the y-axis, definitely not symmetric about the origin. So because of all of those things, we're not classifying this as even or odd. It's neither of those two. Okay. I'm going to let you try example 6. You're going to fill in this table if this is an even function. But I am going to do number 7 with you. Last one for today. If f of x is an odd function and f of 1 equals -4, what's the value of 3 times f of 1 plus 2 times f of -1? Okay, so for an odd function, let's just kind of define some ground rules here. If f of 1 is equal to -4, notice how I'm eventually going to have to do f of -1. So xy would go with -x, -y. F of -1, if it's odd, should be +4. And if you're really unsure about that, make a quick graph and confirm that we have some origin symmetry here, right? So the point 1, -4 is down here, but -1, +4 is up here. Notice how we're symmetric through the origin. Okay, so now that I've defined these two important pieces of information, we're going to do 3 times f of 1. So f of 1 is -4, so plug that in. Plus 2 times f of -1, and f of -1 is +4, so we get -12 plus 8 for our final answer there of -4. So it's not that it's hard calculations, but I think just based on the notation here, if we get stuck on anything, just kind of go back to thinking about what makes something an odd function, and then hopefully you'll be able to do that similarly up here to figure out the missing values for the table in the even function. All right, that's it for even and odd. Of course, we'll do more practice with this next time I see you. Have a great day.